actually several, who they asked, the question that came up was this one here. They were looking at the gold sheet, at least this was one thing that came up on the gold sheet. Hold on, this one. And they saw this formula. No, they saw this one. Come on, brain, work. This, gosh.
That was it.
So they saw this one, and they also saw this one.
Wait, it was this one and then the farther one down.
Okay, there's 4 of them. There's, right here, average velocity. There's instantaneous velocity. There's instantaneous acceleration. And there's also average acceleration.
But they're not the exact same.
Yes, here's why. Listen. No, it's a good question. Look at me. Look. Once you're interacting with me, you get some points, plus it just helps you remember better. Okay, you have been studying slope for a long time. All we're really doing right now is studying slope again. It's just in a slightly different way, but it's really something you have already studied. So it's always easier to learn if you can build on what you already know. Okay? So the thing everyone forgets is slope means rate of change. When you find a slope, you are finding a rate of change. You're finding how fast something is changing. Okay? What you need to memorize for this class is we have been studying position, velocity, acceleration. It's really simple. Let's pull up this, it will help you see it better.
Wait, that does...
We're not studying position, velocity, acceleration?
No, I'm looking at the... Are you looking at the green or the yellow?
This was on the gold.
Gold, yeah. The 2 that I have, it says A of t twice. The 2, there's tangent slope of dt, and then it says tangent slope of dt twice.
So which page you on? Which number, like the number?
24.
So
24?
there's the thing above 16 and the one above 24, and they both are used to find the tangent slope of, which is why I was confused.
Hold on a second.
No, listen, under, at the bottom of the left page.
So you said, give me the 2 numbers. 16 and 24?
Yeah.
They're like the exact same.
So 16 says to find the acceleration. That is, hold on a second. Yeah, to find the acceleration, you find the tangent slope of the velocity. And then on 22?
No,
24, thank you. 24 does say the same thing. I'm not sure why I put 2 of them on the sheet, but
Yeah, that's why I
the
was
same.
just confused.
Second reminder, I don't know. I really don't remember why I had it twice.
Alright.
Is that your question?
I was just confused on that. 'Cause
Oh, yeah, no special reason. So does that answer your question?
Yeah, sorry.
Okay.
Can you trade tally marks between 2 students?
No.
Wait.
No, you can't sell them on the black market. You can't trade them. All of that would be illegal. It's dishonest. Okay. Hey. So I've answered Harrison's question. I forgot as I walked around, was there somebody else who had a specific number, like a whole bunch of things you got to come after school with? There was somebody who's like, I just got stuck on this one thing. We can talk about that with specifically one, please.
On problem 8 on the green.
8 on the green.
Yeah.
Okay, this does fit with what I was saying a minute ago. We've been studying position, velocity, acceleration. Here's how they relate. Keep this open, hold on. Look right here. So look here. Position is simply an amount. Let's go to this one, it'll move easier. So position is simply an amount. Velocity is the rate at which that amount is changing. Rate means slope. So the velocity is the slope of the position. But then acceleration is simply the slope of the velocity. because rate means slope. And acceleration is the rate at which velocity is changing. Questions on that? So now look back here at the one Ethan asked about, number 8. 8 says, what is the average velocity? Stop right there. Okay, velocity means rate, velocity means rate of change in position. So this is saying find the average rate at which the position changes. Read the name for me. Just read the name. Oh. Lydia, read the name. Thank you. Look. Very nice. Clever. Perfect. Okay, so average velocity is the average rate of change of position. The average rate at which the position is changing. The way we find that, so here's the appropriate window on your calculator, because we're trying to go from 4 to 6. So on my calculator, I figure out that over here, the position of the particle at time 4, let's see, got my calculator, okay, window, 4 to 6, zoom fit. So now trace, time 4, position is -132. So back here, -132. And I find the position at time 6, -78. So that's over here. Okay. Velocity means rate of change of position. Average velocity, average rate of change of position. So that means I have to find how much the position changes from here to here. So I'm looking at the position graph, but I am finding average velocity. That's because that's what velocity is. It's the average rate at which the position changes. So I find how much the position changes here. It turns out to be 54. If it's at lunch. Okay, that's not a rate. That's just how much the change was. Rate means, well, per something. So we divide this by 2 seconds, and now we know that on average, your position is changing by 27 meters every 1 second.
Would that be -27?
Thank you, I missed it. Oh no, positive, because we went from -132 to -78, so it did say positive. Good comment.
But if it was like velocity can be negative, but speed can't be.
Correct. The position could be, like if the position had gone down,
Yeah.
then our change in position would have been negative, and our velocity would be negative.
So it would have been, if it was 6 to 4, it would be -27 meters per second.
Yeah, they won't ever ask you to go backwards, but that's the right idea. So, does that make sense? And then here, look, can I clear this? Okay. So this confused some people. It says, what is the secant slope of the position graph? The point of the green, the gold, and the white packets is really for you to gain confidence that you understand how position relates to velocity, relates to acceleration. So I asked a lot of redundant questions, trying to get you to see that they are the same. So number 8, you had to figure out the average velocity. Well, secant slope of the position, that is average velocity. So that was just writing it down. That's your question? Yeah. Let's have a specific number that they really, please brief.
It's more of a calculator user thing, but for 5, 6, and 7, I couldn't figure out how to get to the exact decimal number.
5, 6, and 7 on the green.
Yeah, because I could get close, but not to the exact actual number without knowing it. So.
When you say close, are you like close within like 2 decimal places? The third was just off a little, or?
No, I mean I couldn't actually figure out how to do it, so I was just going back and forth with my cursor on the trace.
Oh, hold on. So like which number did you say? Which number again, Bree?
5, 6, or 7.
5, 6, or 7.
Any of them.
It says use the position graph to determine, I understand your question now, it took me a minute. Use the position graph to determine the time when the particle stops moving left and begins moving right. Here's what you need to do. On the, how should I say, if I look at the big plot that comes with the packet, I can see that that time, and this is what you noticed, is somewhere here. Correct?
Yeah.
To find the exact spot, do this. So this is about 1, 2, 3, 4, 5 something. So we'll go from like 4 to 6. So if I go here, window, we're already 4 to 6. I need to find the bottom right there. So you do this, second calc, and choose minimum. And it says left bound, so you move the cursor to the left of where the minimum is going to occur. Like that. Press enter. Now it says right bound, so move the cursor to the right of where the minimum occurs. Press enter. It asks you to guess. I'm close enough, so just enter. And it tells me the exact minimum. Is that your question?
Yeah.
Any comment? Anybody else? Okay, new stuff. So go to the white packet.
Really tired.
Oh, yes.
I got my back up on Friday. I landed
Let me make a
but then I
note. I
can't
think I'm just going to try to weave that into what we're doing. So you're asking for the difference between
Fired so bad. My back hands first.
this and this, right?
Maybe if I do it all the way down, I'm scared.
It is. Okay, here we go. Okay, first of all, number one. Number one isn't anything new, so you'll just do that at home. Number two.
Here's Danika.
So, the sheet protected item that you received, one comment about this over here. Put it up here on the board, it's easier to see. One second. Okay, this sheet, really, once we discuss and once you do some problems, the goal is to get to the point where all you need on this entire sheet is this box right here. Okay? This is named after a student who came up with the idea. Her name was Danika Wright. So we call this Danika's chart. That's what I named it. Okay, this box here, this is just definitions. You do have to memorize the definitions, but don't memorize them word for word. Just memorize the idea. Okay, the bottom part, that was also created by a student. It's just lots of examples. Okay? The top part is same. So you don't memorize the bottom, but it is a good reference when you're working on homework. You're like, wait a minute, I don't quite understand. Let's go to this big matrix and see if I can see what I'm working on. Okay? Back to the worksheet. Here. Just start reading. The point of the white worksheet is again to help you see how does position relate to velocity relate to acceleration. Like how do they connect? The chart is like a really quick, easy way to see how they connect. So this column is some function, is the column that I will refer to as being the amount. It's not a rate, it's just an amount, like position. Then the rate column is the derivative of the amount. It's kind of loud. Okay, F double prime, F prime prime, means this is the derivative of this column. That's why it's the rate of the rate. Question, please. So derivative is just a fancy word for rate of change at a point, at an instant. It's just the complexity of calculus that they have different words that all mean the same thing, except to learn all the words. So anyway, 2 for Emma. So right here, part 2, A, B, and C. This whole little section is getting you to see how these 2 or 3 things are related to each other. So here we go. The position graph is increasing from time something to time something. So look at the graph. It's the same graph you've done on the gold and the green, so you're getting familiar with it. I remember that all through here, position is decreasing. Okay? But right at this moment, the position begins to increase. So you've done quite a bit of work with your calculator on this white packet. It's up to you. If you want to keep using the calculator to find the precise value, you can. I don't like to assign busy work. So because you've already had a good amount of calculator practice, if you just want to look at the graph and estimate, 4.8, that's good enough as far as I'm concerned. When you check your answer, just make sure you can tell you're right. The window we're working with is only going to go to 7, so we'll just say 4.8 to 7. So the position is increasing from 4.8 to 7. Any questions about that? Please.
Are you saying like on the test where we have to have an exact answer?
So on the test, you would have to find this point using your calculator to find the minimum.
Okay.
For homework, it's okay to estimate and check your answers. Does that answer your question?
Yeah.
2 points for Lexi. Okay. It says, therefore, the velocity graph, okay, here's the connection. Velocity in, this hopefully will answer Emma's question. Velocity is rate of change of position. It's how fast the position is changing. Well, just look at this little section right here. As you follow the curve, just say it out loud. Is the position going up or is the position going down? Say it. It's going up, so it's changing in a positive direction. That means if I found the slope right there, that slope would be some positive value, showing that the position is changing positively. Well, velocity is rate of change of position. So when I see the position going up at all these points, I can be assured that the slope at all those points will be some positive number. That's why this says, therefore the velocity graph is positive. To abbreviate, that's legal on the AP test. For some abbreviation. I'll show you the ones that are legal as the year progresses. So that one's legal from the same time. And Danika's chart says the same thing. It says if you have a graph of an amount that's going up, then the values, the y-coordinates of the rate will all be positive. And if you look here, it lines up perfectly. The exact moment when the position values started to go up was the exact moment when the velocity values became positive. That's what the chart is telling me. Question?
What does the CU and CD stand for?
We'll get there. Wait for asking. Please, Evan.
Why do we end at 7?
Oh, only because I said the window's going to go from 0 to 7. The function itself would go on much further, but it's actually very common on an AP question to say, hey, only look in this window.
Okay.
That's all. Please, 2 points.
What's the I and the D again?
So I is for increase, D for decrease.
Oh.
No worries, keep asking. We'll get to that in a second, although we did use it here. When the position is increasing, the y-coordinates of the velocity have to be positive. Now, here's Emma's question from last night's homework. If I look at this section of the graph, we'll go from 4 to 6 again, since that's already loaded. So here on my calculator, this is from 4 to 6. If I find, let's see, let's copy this over. That off. Okay, if I find, say this, x of, we'll say 6, no, 5. If I find x of 5, that's finding the value of the position at time 5. On this graph, that will be finding this value right here, this y-coordinate. So with the calculator, I can do that, because I can go here, hit trade. Let's just go to the main screen and say, okay, find the position. That's y1 at 5.
Whoa.
So negative 155. That's this y-coordinate right here. Write that down. Okay, if I go find this, I'm getting to your question in a second. This means the tangent slope of the position at time equal 5. That means go find how fast the position is changing at this exact moment. Like how fast is the position changing right there? It means find the velocity. Velocity is how fast position is changing. So to find that slope on the calculator, I go right back to this screen. Instead of doing y1 of 5, I do derivative of y1. So like this. And I do that at 5. That value is 14. Okay, back to here. So that means the slope right there is 14. Well, slope of the position is the velocity. So up here, I'm probably doing more than you need, but just be patient. I can find the velocity again on my calculator by doing velocity, that's formula 2, at 5. 14. Does that make sense? And then I can do the same thing with these two. I can find, so now I know over here, let's see, the green one was position at time 5. That's negative 155. I should have color coded these better. The tangent slope down there is 14. The velocity at time 5 is therefore also 14. We checked that. If I go find the tangent slope of the velocity at 5, I'll be finding
the red line is, right?
Perfect. I'm going to find this slope, and that will be this y-coordinate. That's the whole idea.
Whoa!
Did I answer your question?
It just clicked.
2 points. Okay, everyone in the room, look. Okay, if that doesn't make sense, you've got to either talk to me or come talk to me in a smaller group. Like the whole class is built on that. Like this is not a math class, I think I mentioned to you, where we do a little unit, you're like, okay, I struggled with that unit, no big deal, I'll just do good on the next unit. No, you can't go forward. It's like, this is really like a language class, where if you don't learn the language as the days go by, in November, you don't even know what I'm saying anymore. So questions here, you may need me to repeat anything. Awesome. So back to here. So can I clear this? Come on. Okay, so back to this. So you know the position graph is increasing. Got to rewrite it. Hold on. From time equal about 4.8 to time 7. Therefore, the velocity graph is positive over that time. Okay, new definition. It's on your sheet. So if you look at your reference sheet and I say what you're about to look at, you'll remember it better. Okay, if you look at the top box where the definitions are listed, one of the definitions talks about relative max. I believe it's bolded. Okay, I'm going to give you the definition for relative min. I didn't print it because it's just the opposite. So it says something like, any function has a relative or local min when that function changes decrease to increase. Everybody see that? So that's what this is talking about right here. Therefore, the position. Therefore, the position function has a relative or local min. Again, we're stuck with learning both words just because somebody couldn't agree on one word. Relative or local min, you can abbreviate minimum, you can just write min, is fine. At that time. Any questions about the definition for relative min? Okay. Notice the sign here, graciously donated by Reese Curtis last year. Okay, it's very serious. You cannot use the word it on the AP test. That's not my thing, that's the rules. Like, you use the word it as you explain things, highly likely you're losing points. You've got to be very specific. So if you notice in that definition, I did not use the word it at all. I said any function has a relative min. I didn't say when it changes, and when the function changes, decrease to increase. You've got to be very specific about what function you're talking about. So right here, I would say the position function, you can just say position, has a relative min when position changes, decrease to increase. We'll look at the definition again. Then there's a big or. It says or when that function's derivative changes negative to positive. You look at the board or your paper and notice. At the moment, we've talked about this already, at the moment when the position is changing from decrease to increase, that is exactly the moment when the derivative of position, velocity, is changing from negative y coordinates to positive y coordinates. Danika's chart says the same thing. When the position changes decrease to increase, the y coordinates of the velocity change negative to positive. Okay? That is talking about a relative min on position, not velocity. Question, Harrison?
Is it possible for the red line to have a derivative?
It is. The red line absolutely has a derivative. The name is not something we study in our class, so we don't worry about it. But sure, there's a rate at which the acceleration is changing as well.
That's you.
Thank you.
So what's the derivative again?
So derivative means rate of change.
The rate of change is slope.
And rate of change is slope. Perfect. And if it's a rate of change, Amanda and Gil, points for both of you. If it's a rate of change at a moment, like an instant, that's instantaneous rate of change. That's a derivative. Average rate of change is still slope, just slope between points. That's secant slope. Danny, please.
So they don't call the average rate of change a derivative? It's
They do
only
not.
instantaneous?
Yeah, average rate of change is not a derivative. Derivative is a change at a given instant. Good question, 2 points. Somebody else? Awesome. Okay, another definition on your sheet. So look at your references. I can quote it for you. There's a definition there that says critical point. Okay? It says something like this, and probably saying almost word for word. Am I doing a decent job?
Yeah, it's ridiculous.
Good.
Incredible.
Any function, okay, has a critical point when that function has a tangent slope. Notice I did not use the word it. When that function has a tangent slope that is 0 or undefined. So look here on the graph, and notice the position function has a tangent slope of 0 right there. The slope at that point would be 0. The rate of change is 0 at that instant. The graph at that instant is not going down, it's not going up. It's just sitting there. Go ahead.
Would it not be a number at all?
The rate of change is actually 0 at that one instant. Just at that one instant, you're at the very bottom. You're not going down, you're not going up, you're just at the bottom. Question? Important.
Does that mean that critical points are only in either where the line slope changes from positive to from negative to positive, but also like when it's a max or a min?
So let me say it back to you. Let's just keep talking here for a minute. So the position graph as shown, make sure this makes sense and we'll get to Matthew's question. The position graph as shown has only one critical point. Right here it's a little bit unclear, but when we zoomed in doing the last homework, we noticed that the position does not go flat. It's still going down. So nowhere along here does the position have a slope of 0, ever. Except right here, so that's a critical point on position. The acceleration has a critical point. It's right there. The velocity has 2 critical points. Right here and right here. Questions?
So it is where the slope changes from either a positive slope to a negative slope, or from a negative slope to a positive slope.
Look over here and it'll answer that question as well. Okay, so the position will have a critical point when the slope of the position is 0 or undefined. And then there's a big or on your reference sheet. Or where the function's derivative has a value that is 0 or undefined. So what you're noticing is, hey, these tangent slopes, they're all negative because the position's going down. These tangent slopes are all positive because the position's going up. That means the derivative, look right here, velocity. These values are all negative. These values are all positive. That's exactly what you're saying. Please, Danny.
What would a critical point look like when it was undefined?
So, 1 second. Don't forget your question. I gotta do one more thing with math. You can have a function that does this. The function can come down, actually go flat for one point, and then continue downward. That also is a critical point because the slope of the function is 0. So that's another way to have a critical point. Undefined would be something like this. If the function goes vertical for a point, then the slope right at that, the slope right there where the function goes vertical, that's an undefined slope. That would be a critical point on this green function. There'll be some other ways we'll show later, but enough for now. So, for Danny. Okay. I would say the most common error with critical point and even relative min or max is Danika's chart shows you how those things interact with each other, but you can't like get it backwards. This point right here, that's a critical point of position. It's where the position's derivative is 0. But it's not a critical point on the velocity. It's a critical point on the position. Okay? On the test, what's most likely to happen is they'll give you the velocity, and they'll say, find the critical point of the position. So I go find where the velocity is 0. That's where position has a critical point. And you need to say that again. So what will confuse people is, on a test, they might give you the velocity. And they'll say, where is the critical point of the position? So you look at the definition, you say, okay, trying to find the critical point of the position. So I remember the definition. The position has a critical point when the tangent slope of the position is 0. But I don't see the position on my test question. I see the velocity. Oh yeah, the definition says, or the position will have a critical point when the derivative of position, that's velocity, is 0. So that's the moment when the position will have the critical point.
So the derivative of position is velocity.
Correct. The derivative of velocity is acceleration. Keep going.
But is the tangent slope of position, isn't that velocity?
Same thing.
Okay.
Yeah, no, good question, Mario. Derivative and tangent slope are the same thing. Derivative and tangent slope are the same thing. The goal packet mentioned that, but it just takes a while to get it to sink in. So you're fine. Just keep asking. 2 points for Mario. That's going to happen at the same time. This is what I just said to Marielle. The position has a critical point at time 4.8 because the velocity at that time has a value of 0, like that. This is another one of those worksheets where you do not want to check your answers casually. Like, you got to make sure you have it dead on. Like I said earlier, the number isn't so important as long as you're, right in the vicinity. But you can't read that casually. The position has a critical point when the velocity is 0. We want to talk more about critical points or relative linear math. Okay, next one. It says the velocity graph is increasing from time 0 to what time? So we need to look closely here, so you may need to use your calculator. So here we go. Window, I think 0.3 was about right.
You did 4 to 1.
Shoot.
You did a 4.
Dumb calculator.
0 to 0.3.
There we go. Operator error. Shoot.
Wait, what is it?
0 to 0.3, sorry. Now I can see it. So the question says, velocity is increasing from time 0 until when? So I can see it now. Velocity is going up. Probably get to somewhere in about here, so pretty close to 0.2. So back to the worksheet. The velocity is increasing from 0 to about 0.2. You need me to talk more about that? Therefore, look over here at Danika's chart. Let's see, velocity. The velocity is increasing from 0 to 0.2. Therefore, the acceleration must have positive y-coordinates on that same span. So the acceleration graph has to be positive for that same section of the graph. If you look up, you can see it right here. The blown-up version is a little more clear. It was exactly the moment when the acceleration stopped having positive values. All of these acceleration values are positive. Right there, acceleration switches and becomes negative. That's the exact moment when the velocity stops going up and starts going down. Danika's chart shows you that.
How do we know it's 0.3?
I don't know exactly. I could find it on the calculator by doing this. I could say, hey, let's go find the 0 of the acceleration.
Right.
So just go second calc, 0. Choose the appropriate graph. I need the acceleration. So I do the left bound here. That's good. Right bound. 0.202.
Yeah.
And then yes. Perfect. 0.202. Please.
Can you kind of explain how you see that on the chart?
Uh-huh.
The acceleration.
So what I did is from my calculator, I saw that the velocity is going up. Let's pull this over. Come on. Okay. Yeah. So here's the blown up version, Mario. So I can see from here that velocity is going up. It says on the chart that when velocity is increasing, meaning the y values go up, the y values of the acceleration will have to be positive. when the velocity values start to go down, the y values of the acceleration will have to be negative. That's because acceleration is the slope of the velocity. So if I follow here, I notice that each of these little slopes of the velocity, they're all positive. They're all pointed upward. When I start going back down, they start to slant downward. That's the exact moment when the values of the acceleration change from being positive to being negative. 2 point. You want to need more talk here? Please.
So, like the minimum of the acceleration, what is that in velocity graph? What is that?
So, 2 for Adam. Actually, I want to call room to answer this. So based on what you see in the chart here, 2 for Adam, it's a good question. What you see here, let's see, acceleration, so remember the definition. Acceleration would have a relative min when the acceleration changes, decrease to increase. So I'm looking for that. So please raise your hand if you can tell me. Feel free to talk to each other. What would be the corresponding, so that's when the acceleration has a relative min. What would be the corresponding change on the velocity graph, according to Danika's chart? The whole point of the chart is to show you that when one function does this, the other function does something else, but they correspond. So when you see the acceleration right here in red,
What does CU or CPU mean?
concave up, concave down.
Oh.
So when you see the acceleration having a relative minimum about right here, acceleration is changing from decrease to increase. What change is occurring on the velocity graph according to Danika's chart? We went decrease to increase. What change is occurring according to Danika's chart on the velocity graph? If you're not raising your hand, you're either just tired, shy, or overthinking it. What's happening, Paul?
It's on the velocity graph, it's like it's
Perfect, it's right here. The velocity graph will be changing from a concave down shape to a concave up shape. How many knew it? 2 points, 3 for Paul. It's right here. Here the velocity is concave down. Here the velocity is concave up.
Is any of that information represented on the blown-up graph? Or is
This
that-
one here?
that should we not be looking at?
This one is pretty hard to see because it's zoomed in so far.
Okay.
In fact, we can't see it at all because we can't see the relative min of the acceleration. So we're just looking like right here on the blown up version. So we can't see this, so no. Good question. Point? Adam, I don't know if that answered your question. Okay. Please.
Okay, so the relative min
Of what?
of the acceleration, how did you see that from the increase and decrease?
So first thing is I got the definition memorized, that the acceleration will have a relative min when the acceleration changes, decrease to increase. So then I look at the graph and say, hey, right here acceleration is decreasing. Oh, now it changes. Now acceleration is increasing. So that's the relative min of acceleration. 2 points. Okay, next page. Oh, please.
What significance does the concave up or concave down have? What does that tell us?
So the word concave up literally means the slope of the graph is increasing. So watch.
Whoa.
This is the acceleration, right? On this picture, the acceleration is always concave up.
Right.
Agreed?
That's crazy.
Watch the slope here. So if I draw slopes right here, please say out loud, is that slope positive or negative? Say it. Negative. One more time, is that slope positive or negative? Negative. It's pointed down, it's negative. I follow the curve to a new spot. That slope is still negative. Careful, listen closely. I want you to say more negative or less negative. Say it.
Less negative.
Good. So this slope is negative, this slope is less negative. did the slope of the acceleration increase as we followed the curve? Yeah, it went up. Went from very negative to less negative. Go to a new spot. Positive or negative, say it. Negative. Less negative or more negative. So as I follow the acceleration curve, I'm seeing that the slope of that curve is increasing. Right here the slope is 0. Now the slope is positive. Now the slope is even more positive. Concave up means if you follow the curve, you will see that the slope of the curve increases point by point.
So
That's,
even,
go ahead.
So even though the slope is negative, it's always increasing.
It's concave up.
It's concave up.
Yep. That's what concave up means. So look at Danika's chart. The chart is a staircase. Can you see the steps?
Yeah.
Okay? So you can build the chart as far as you want. So I can put right here, positive, negative like that. I can put right here, concave up, concave down. And increase, decrease. And this column would become A prime, which is the slope of A. So the chart says exactly what we just said. When the acceleration is concave up, the values of the slope of A will increase. Please.
Is it getting less negative because it's like starting to flatten out that way?
Perfect. 2 points. Okay, we good? Good questions. Next one. 3. Okay, lots of blanks. So you've got to kind of see what the worksheet's trying to get you, like what kind of connection is the worksheet trying to get you to make. So it's obviously comparing velocity with acceleration. So it says the velocity graph is decreasing. Okay, I got it. Velocity was increasing to 0.3. So now the velocity is going to decrease from 0.3 to about here. Again, I don't want busy work, so and that's 3.3 is about right. I don't know what the back says, but is that okay to there? Therefore, Danika's chart, the velocity is decreasing. Yeah, that's easy. The slopes of the velocity are negative. Acceleration is the slope of the velocity.
This is crazy. Math words.
This is why people say calculus isn't math.
It's just observation.
It's not plug and chug. It's, okay, honestly, it's like real math. It's like, do I understand this? Can I use it for something? Can I put the pieces together and gain some real knowledge, not just a recipe book? So,
Where would you use this?
so honestly, the hardest thing about that question for every math beyond like elementary school is that most of it is only heavily used if you go into, you know, engineering, computer science, hard sciences, honestly. Economics, finance. I talked to Connor Humphreys the other day. He's a coach here, was my student a long time ago. He's in economics at BYU, heavily using calculus to do economic modeling and that sort of thing. Anyway, we're kind of short on time, but okay. Oh, please. Negative. It's okay. Yep.
Is that inappropriate?
Hmm? Yeah, I'll try pretty hard, Jack. You keep reminding me to not, like I'll try pretty hard to only use the abbreviations that are valid. Once in a while I use one of mine, I'll try to warn you, that's just mine. So. These are valid, they accept CU, CD. The I and D, better to say INC just to be safe. So
Why I and C?
for increase.
Oh,
And
I thought you
decrease.
said I and C.
Oh, gotcha. Okay, look. So we figured out this. So the acceleration graph is negative from same time period. The function v of t. So they're looking right here on velocity. They're noticing, hey look, velocity goes up, velocity goes down. So velocity has a relative or local minimum.
Why is it minimum?
Oh, max, sorry, thank you. Scary. F 0.3, my bad.
There could be a minimum.
Absolutely, right here. In fact, Jackie, on a worksheet like this where there's lots of blanks, if I were doing the homework and I just happened to look here and write that it was a local max at 3.3, and then when I turn to the back, I go, oh yeah, that makes sense. I wouldn't even worry about it, I just go on.
Yeah.
Because like, okay, I understand.
It's not giving you it.
Yeah, you don't have enough information to know which one they're looking for, so. Anybody else? Okay. V of t, therefore, has a critical point.
What's a critical point again?
So I'm just going to quote the definition just to help you remember it. So the definition says, any function, in this case that's velocity, so velocity has a critical point when the tangent slope of the velocity is 0 or undefined. So right here, tangent slope of the velocity is 0, and coincidentally the value of the acceleration is 0. So that's this part. So critical point at 0.3, therefore the value of the acceleration at 0.3 must be 0. Perfect. Number 5. 4 minutes to go. Okay. This one's relating acceleration and velocity, and they're relating the concavity. So I'm going to kind of use that as a hint to help me fill in the blanks. Let's see, velocity and acceleration. So here and here, the velocity graph is concave, so they're looking right here. So let's say the acceleration graph is, oh I got it, decreasing. DC is acceptable. So the acceleration graph is decreasing from 0 to, I think the back actually says 1.75. Therefore, the velocity graph is concave down on that interval, 1.75 here. And you can see it. Here the velocity is concave down. The exact moment when the velocity, when the acceleration switches from decreasing to increasing, that's when the velocity switches from concave down to concave up.
Wait, why is it only decreasing at 0? It looks like it's decreasing all the way up there as well.
So the acceleration is decreasing. The values are getting lower and lower, less and less, to here. Do you agree?
Yeah, but why does it only start at 0 if it was decreasing at negative?
Oh, my bad. Sorry. Only because the window I gave you started at 0.
Oh, okay.
Yeah. Good question. 2 points. Anybody else? Awesome. Go to 6. The acceleration graph is something. Oh, they're comparing concavity again. So let's see.
Increasing.
Oh, increasing. Thank you. So acceleration graph is increasing from 1.75. It does, but we'll stop at 7 because that's the window we stated at the start of the problem. Therefore, the velocity graph is concave up over that time period. Questions on that? Please.
know it's asking you increase or decrease?
The only reason I know that is I know they're talking about acceleration and velocity. So I'm over here looking at these 2 columns, and then I notice that they're asking something about the concavity of the velocity. So they're looking here. Good. So okay, got it. They want me to, and it's also just kind of reading, like the worksheet just follows the graph. So here, we talked about how the acceleration is decreasing to 1.75. Then on the next question, oh yeah, just follow the graph. Go ahead.
How come, could you have done increasing before?
You could.
Okay.
Yeah, there's nothing special about that. That's kind of like I said to Jackie, that's where fill in the blank can be ambiguous. So don't stress about that. So. V of t therefore has a critical point. No, new word, inflection point.
Oh, joy.
Oh joy.
Inflection point is just a spicy way to say critical point.
No.
Spicy.
Good question, no. Hey, inflection point's a new thing. It's on your sheet. It says any function has an inflection point when that function changes concavity. So the velocity changed concavity at 1.75.
What does it mean to change concavity?
So the velocity is initially concave down. At about 1.75, velocity changes to concave up.
So we're not looking at the acceleration graph, we're still at the velocity.
At that point, just velocity, but now it asks you to connect. So the next line says, oh, what happens to the acceleration at that point? Look here. When velocity is changing concavity, meaning velocity has an inflection point, the acceleration is changing increase to decrease, or vice versa. You can see it. Acceleration is going down, acceleration goes back up. So when the acceleration does that, the velocity has an inflection point. Good work.
Inflection point is when it causes the acceleration to change.
You have to be a little bit more specific. The inflection point on the inflection point on the velocity is when the acceleration changes.
You're gonna try to.
Actually, so